Hello everyone. In this video I'm going to go over today's class notes with you, which are about histograms, and so we'll learn some concepts and vocabulary words together, and then I will show you some examples of how to do things in Excel, and that will prepare you for your homework and your quiz during next class. Okay, so today we're going to learn how to make grouped frequency distributions for quantitative variables. We'll learn what a histogram is, some words to describe the shape of histograms, and how to make histograms for quantitative variables in Excel. So last time you might remember that we did frequency distributions. So when you have a qualitative variable, then you can make a frequency distribution showing how many of the observation units had each category for that variable. But it's a little bit harder to do that sort of thing for quantitative variables because there can be so many different values. So what we do is group the different values into intervals or bins, and then we make a frequency distribution from that, which can be called a grouped frequency distribution. So let's look at a small example here. On our class survey data, one of the questions was how long it takes for you to get ready in the morning between waking up and leaving the house. So here are 10 randomly selected answers from that question. So these are in minutes. And what we can do is, well, if we wanted to just make a frequency distribution showing every different answer, it would be really boring. It wouldn't be much more useful than just looking at these 10 numbers. But what we can do that's more easier to understand is a grouped frequency distribution. So for example, for the different answers, we could have the ones that were 0 to 19. So there were 2 people that answered between 0 and 19, this 2 and this 15 here. And then we could have the answers from 20 to 39. There were 4 answers like that. And then from 40 to 60, and there were 4 answers like that. Okay? And there's different ways we could group the different values. So that was in 20-minute intervals, roughly. We could do it in 15-minute intervals instead. So there were 2 people from 0 to 15, 3 from 16 to 30, and so on and so forth. Another way to write these groups, here I'm just using the word 2, and I'm sort of including, which implies in English that we're including the endpoints. Like in this group here, 0 to 19, we would include 0 and 19 in that category. But another way to write the groups or the bins or the intervals is using interval notation. So this notation, you might have seen it before if you took calculus or pre-calculus. You use parentheses or square brackets. So everything between the 2 numbers is included. Things that are strictly between them are included. And then if one of the ends has a square bracket like this, then we include the number that's next to that. But if one of the ends is a round parenthesis, we do not include the number next to that. Okay, so for example, if I look at this interval here, parentheses 0, 20 bracket, that would include 20, but it would not include 0. So if somebody answered 0 on a survey question, we would not count them in that category. On this one from 5 to 12, this would include 5. So if someone answered 5 on the question, we would include them in this category. But if they answered 12, we would not include them. There would probably be a different category that would have 12 in it. It's not this one. But if they answered anything up to 12, like 11.9, 11.99, we would include them in this category. Okay, I hope that's making sense to you guys. Using these intervals and this interval notation allows us to be able to categorize any numerical value, not just integers, because people could answer between integers, right? So for example, we could redo the frequency table up here, this one, we could redo it like this one down here. So instead of saying 0 to 19, we could use the interval including 0 but not including 20, and then that would allow people who took like 19.5 minutes to be in that category. Whereas up here on this original one, there was actually no place for someone who took 19.5 minutes. There was no place to categorize them. And then we have from 20 to 39, we can redo it with this one from 20 to 40, but not including 40, but we are including 20. And then for the last one, I mean, we have to put 60 somewhere. So unlike the first two intervals, this has two square brackets. You'll always have one interval that's like a little bit different from the others because the endpoints have to go somewhere. So this includes 40 and 60 and everything in between. And this is just another way to redo this first table up here. You'll see in this one, I just kind of randomly made all of them end with a square bracket. So we are including 30 in this category. We are including 45 in this category, but not 30, and so on. All right, so that is interval notation. Now the intervals themselves are also called bins. So you kind of imagine that you have like these bins or baskets or boxes, and you're just kind of like taking everyone's response and throwing them into a different bin to categorize them. So the intervals are called bins, and the bin width is the difference between the upper limit and the lower limit of the bin. So for example, the bin not including 30 and including 45, so the bin from 30 to 45, including 45, that has a width of, it's just the larger number minus the smaller number. So 45 minus 30, that's 15. So larger minus smaller. It's really important when you're making these grouped frequency distributions that you use a consistent bin width. And the reason for that is because that is what humans expect when they see this type of frequency distribution. They expect it to be done evenly. And if you don't do it that way, but they think that you did, then you could actually mislead people. That would be an example of lying with statistics. So we don't want to do that. All right, so once you have a grouped frequency distribution, in other words, a table like one of these, you can use it to make what's called a histogram. So this is a chart, and it's basically just a column chart, but the only little difference is that the columns have no space between them. And that lack of space suggests the concept of continuity, which makes sense for numerical data because, for example, on this minutes to get ready question, somebody could have answered anything from 0, well, all the way up to infinity, I guess. Like there's no number in there that they couldn't answer. So everything is available to them. That entire continuum from 0 up to, I don't know, whatever a reasonable answer is. Like the largest one in our class was 2 hours. Right, so that is a histogram. And then the choice of bin width or the number of bins has a really big effect on how the histogram looks. And there's no like one single right answer for how many bins you should use or how wide you should make them. There's some kind of like rules of thumb, none of which are really that great. I think I don't even want to teach you guys one rule of thumb because honestly, you should just try some different histogram bin widths and just see like what best summarizes the data. So here is the minutes to get ready data from our class survey, and I've done it with 3 different bin widths. So in the first one here, you can see the bin width 5 to 35, that's a bin width of 30. So I'm using half-hour intervals. And I think this summarizes the data pretty well. You can see that the vast majority of people are, this looks like about 2/3 of the people are between 5 and 35 minutes to get ready. And then there's another, about 1/3 of the people take 35 to 65. And then there's just like a few people that take a little bit longer than that. So that's a pretty good summary of the data. Oh, I think this is the data prior to you guys being in this class, by the way. So it's not the full 200 responses. The second histogram here, it's a bin width of 20. And this also does a pretty good job, maybe even a better job than the first one, because we can see more details. So it looks like, now it's a little harder for me to tell percentages. The most popular time to get ready was 25 to 45 minutes. Slightly less popular was 5 to 25. And quite a bit less popular is 45 to 65. And then there's just a few people, like maybe one person each in these other 3 bins. So that also does a good job of summarizing the data. I think you can pretty clearly see just from looking at it, like how long most people are taking. This last one here, you can see what happens as you keep making the bins smaller. This is 5-minute intervals. And I mean, it's the same data and we're getting a lot of details, but it's kind of hard to like make sense of this. There's just too much going on here. It's not really a summary anymore because there's too much information. So you guys can see there's like kind of a sweet spot between too little information and too much information. And there's no like hard and fast rule of how you find that sweet spot. Just have to try some different bin widths and see what looks good to you. All right. I know students hate it whenever I tell them things like that. Like, just try it and see what you like. But that is the real answer. There's no one correct way of doing it. Okay, so once we have a histogram, it's really common to talk about the shape of it and how it looks, and there's some common words that are used to describe histograms. So I'm going to give you some of those with some examples. And in these discussions of histogram shape, the words histogram, data, and distribution can be used pretty interchangeably because the histogram is really just a picture of your data. So you can talk about the histogram or you can talk about the data itself. And then this word distribution, that is referring to, if you come back up here, like that is the tables that we were making, frequency distributions. It goes back to that concept of like having your bins or your categories, and then you're throwing each response from the data into a different bin. So you're distributing them to the bins, if that makes sense. So that's where that word comes from. And those are used pretty interchangeably. All right, so some vocab words. The mode, you might have already learned in some class that the mode is the most common value. It's a little bit more complicated than that. Because with quantitative data, it's entirely possible that everybody gives a different answer, right? So there might not be a most common value, but when you've made a histogram, you have intervals and you may have a most common interval. So for example, in our shoe size data from the class survey, the most common interval for this particular histogram was 8.5 to 10, and that was not including 8.5, but it is including 10. So I think everyone answered in half sizes or whole sizes. So that would have been the bin that included 9, 9.5, and 10 for shoe sizes. That was the most common response with almost 60 people. So that would be the modal bin, or you could just call it the mode. And then as far as modes go, you can have more than one mode. So this is another kind of concept that's not really discussed when you're talking about mode as just the most common value. But when you're talking about mode as bins on a histogram, you can have more than one mode. Even if they're not the same height, you can have different regions of the histogram that have peaks. So here's a really good example. This is the fish sample data from the Freshwater Research Institute, which is our SU research institute on, well, freshwater. So we have this huge collected data set from a whole bunch of different colleges and universities where they've been collecting data for, I think, about 15 years now. It's all been collected into one data set by Matt Wilson, and he's made that available publicly, so I'm using that for some examples in this class. This data set has 13,000 fish in it, and they were measured in about how many? I think about 2,000 different events where people actually went out into the field and, collected the fish, measured them and put them back. So anyway, in the fish data set, we have these fish lengths, and you can see there's really clear bimodal distribution where there's two distinct peaks. It's quite clear from looking at it. And a lot of times with bimodal, it may be because two different groups were mixed together. Like this could be male fish and female fish. I actually really don't know. I mean, I don't think trout are that much bigger in the male and the female, so I actually am not sure why this bimodal is here. I originally thought it might have been two species, like brown trout and brook trout, but later on, I actually, after I made this picture, I checked and it's not the two species. So I started to think it might be native trout and stocked trout, but I'm not sure about that either, honestly. So I really don't know where the bimodal thing is coming from here. It's like a mystery for now. Maybe I'll have to ask Matt Wilson about that. But yeah, you can clearly see these two peaks. In addition to bimodal, you can have like trimodal or just multimodal, just more than two clear peaks. Okay. Oh, and by the way, when you're talking about like modes and peaks, They do need to be like pretty isolated from the nearby bins. Like, just for example, looking at this shoe size data here, there's one bin over here that's like slightly taller than its neighbor, but I would not refer to that as a peak because it's just so close to the next one. A peak really needs to be kind of like isolated. It needs to have some slopes leading up to it, like a series of bins that are getting taller as you go up to it, like these three right here. Okay. Tails. We can have left tails, we can have right tails. So the tails are the parts of the histogram where you have a whole bunch of shorter and shorter bins that are stretching away to the left and the right. This is a commonly seen feature on many histograms. And the meaning of these bins that I've circled here, or the tails, is that basically you're having these categories, these bins, that are getting less and less popular as the values in them are getting larger. So looking at the water temperature here, this is from the fish sample data. Every time they went out and measured some fish, they took the water temperature where they were doing it at. So these are all the water temperatures. And what you can see is that most of the water temperatures were between about, what is this, like 12.5 to 18.5. And then as you get into higher and higher water temperatures, they're getting less and less common, less and less popular. So those would be like uncommonly large values. I believe these are also in Celsius, so Celsius temperature of 30 is like really pretty hot for water. Okay. We can also describe tails as fat or thin, or you can use the word heavy instead of fat if you want to. Fat just means there's more height to the bins, and thin means there's less height. So when we look at this picture here of the water temperatures, we see a short left tail. It doesn't stretch out very far to the left, and we have a long right tail. Next is outliers. So outliers are values that are far away from the rest of the data, even more so than the tail. And outliers, you can usually classify them as outliers because there's some gap before you get to them. Sometimes it can be hard to tell the difference between a tail and an outlier. Like with these water temperatures here, in this really, really thin part of the tail towards the right, maybe we could classify those as outliers. It's not really clear whether that's a tail or just a few outliers. But this example down here with our heights from the class survey, there was that one person who said that they were 7 feet tall. That's definitely an outlier. By the way, I never got that person. It was a previous class and I never got anyone to confess. So I think it might have actually just been a typo. And that is something that can happen is recording errors. There are some in the fish data too. Like there's a few places where people said the pH was 0 or whatever, like physically impossible thing to have happened. Like, how did you even put your measuring instrument in a solution that acidic? You would have melted it. Right, so those are outliers, data values that are really far away from the rest. And they can often appear kind of like a bump at the end of a tail, where there's like a gap with 0 height bins in between. Okay, some more words. There's a lot of these, sorry. But people do talk about all this stuff commonly. So a histogram is symmetric if it's symmetric from left to right. That's what that means. The dissolved oxygen data from the fish samples. Sorry, people are clearing snow outside. I don't know if you guys can hear that. This is a fairly symmetrical distribution here, I would say. It's not perfect, but it's pretty close. It's the tail on the left, I think, is a little bit fatter, but other than that, it's pretty symmetrical. What else? Oh, yes, skewed. So if you're not symmetrical, then you're probably skewed. You can be skewed left or you can be skewed right. And the direction right or left actually refers to which side has the longer, fatter tail. Okay, so if your right tail is longer and heavier, that is skewed right. And if your left tail is longer and heavier, that is skewed left. So it's the direction of the tail. And that's kind of counterintuitive because a lot of times people want to focus on like where most of the data was and use that direction. Like in this first example here, most of the data, most of the responses or the measurements were towards the left side of this histogram, but the direction of the skew is towards the right. And the reason we say it's towards the right is because that's where those kind of unusually high or unusually low values were for this particular instance. They were high values, so that's towards the right. When you have skewed data, we've talked a little bit before about how unusually large values can drag the average up, because when you're taking the average, you have to total all the values. So if you have one or two huge values in there, that can make the average really, really large. And in the opposite direction as well, if you have one or two really small values or negative values, that can also drag the average down. Whereas the median is not going to be moved around too much by unusual data points, because you're always going to the middle of the data for the median. So those unusual values are nowhere near the median. So you can see in this one, for example, where it's skewed right, those unusually high values in that long fat tail are dragging the average up to be higher than the median. So the median is 16.5, and the average was median was 16.15, the average was 16.52. We see the same thing when it's skewed left. The average will be dragged to the left or dragged down by that long fat tail to the left. Okay, so the pH data from the fish sampling was skewed left. All right, another type of distribution is uniform distribution. That's when all the bins are about the same height, and they don't have to be perfectly the same height. You see these ones here, like it's not exactly, there's a couple that are lower, but it's about uniform across the top here. I couldn't find a uniform distribution in any of our data sets that we've been looking at, so I just pulled this one from the internet. It's from someone's research paper. Okay. Bell-shaped or normally distributed, this is the last one. We'll talk about this a lot more in this class, but bell-shaped means it's roughly got that kind of curvy bell shape. It's generally going to be roughly symmetrical. It has one peak in the middle, and it's got these S-shaped kind of sides where it's like it's curving up and then it's curving down, and it's going to have long, thin tails as well. So this is a really commonly seen type of distribution, which you'll get to find out so much about why we see this all over the place. It's pretty interesting. The dissolved oxygen measurements from the fish data was the clearest bell shape that I found when I was making these examples, for whatever reason. Okay, so we also have an example file for us to play with and make some histograms. So I'm going to go ahead and do that. And then these instructions are here in case you get lost or you kind of just want to read over them later. So I'll just switch to the Excel file now. Here it is. So we have 3 tabs, and I just left the quantitative data for the most part in these. So we have class survey data, we have SU sections data from section search, and then we have, this is from the fish data set. It's not the 13,000 fish. This is the 1,307 fish events, which are the events where someone went into the field and started measuring some fish. So they didn't take the water temperature every time they grabbed a fish. They would just do it like once at the beginning before doing all the fish that were there that day. Okay, so starting with the class survey, how do we do a histogram? So first of all, we cannot actually do that table part like at the beginning of the notes where I was writing down the intervals and then putting the counts into a table like this. Unfortunately, it's just not a thing you can do in Excel that I know of. If they've added it, then let me know, but it's never been there before. So you can make a histogram, though, pretty easily. So just select the column that you want to make the histogram from. I'll just do the total height column here. I've got it sorted from greatest to least, so this 8-foot-tall person is at the top. So I'll just click on the E above it and then go to Insert. And there's 2 options here that look similar. One is the column chart. That is not what you want. Histogram is the one that you want. So it looks like all the columns are the same color, and it should actually say histogram above it when you click the drop-down menu. Okay, So you're going to do histogram. Don't do Pareto chart. That's the second one there. You're going to click histogram. And it takes a second. Okay, so here is our height data. So you see the person that said they were 8 feet tall is over here in this bin by themselves, far away from everyone else. And everyone else is over here in a group. So Excel has automatically chosen the bin width based on some considerations of its own that I don't know about. And a lot of times you might not like that bin width, or you might not like the number of bins. It also doesn't do the default title up here, so you should usually change this to, you know, something more sensible. If you want to change the number of bins or the bin width, you're going to right-click right on those bins, on the numbers in the bins, and do Format Axis. If you're on Web Excel or iPad Excel, it might be somewhere else, I don't know. Okay, so right-click, Format Axis, and that should take you right to the menu that has the bin widths and stuff. If you get lost in these menus over here, it's this, you have to click on this little icon here that looks like a histogram, not these paint cans and stuff. And then it's under Axis options. Okay, so you can do automatic, or you can click bin width and change it yourself. So I could put 2 in here, for example, and then hit enter. Now you can see all the bin widths are 2. Or we can change the number of bins. If I change the number of bins to like 25, for example, you see when I do that, it's like picking some, it's kind of like taking the highest value minus the lowest value and then just chopping that into 25 pieces. And that can mean that you have some kind of weird looking decimals. So I usually do the bin width and like try to put it on kind of like a round value. Maybe 1.75 would be closer to something that would look nice, or 1.5 maybe. So you cannot set both of those things. You have to pick one or the other. There's also an option here for an overflow bin or an underflow bin. So this actually is a good example of one where you might want an overflow bin. Like maybe you just want to take everybody that said they're 7 feet tall or over and stick them into one bin. Let's see, what's 7 feet tall? 7 times 12, 70, 84. So we could put everyone that's 84 inches or higher into their own bin, which is just this one person that lied about their height. So that kind of allows you to make the rest of the histogram like spread out a little more. And you can also do an underflow bin that does the same thing, basically, but we don't need it for this one. Okay, so the rest of it's a little more stretched out and looking nicer now. Right, so that is how you make a histogram and change the options for it. And other than that, it's pretty much just like you need to learn the vocab words and describe the histograms with them. So I will post up some homework and solutions as well, and you guys can use that to prepare for the quiz next time. Alrighty.